Hello and welcome to this Isaac Physics online tutorial, which will run for approximately 30 to 45 minutes today, where the topic will be exponentials. And before I say anything else, let me remind you that in order to ask me questions today about what we're going to do, you're going to need to log in with your Isaac Physics account, and that will allow you to use the app that you see at the bottom of the page for this event to send me questions as we go along. And please do send questions if you have any, because it's quite likely that I might make a mistake in my working, and if you do spot it, then it'll be very helpful for everybody else as well that you pointed out to me, or if any kind of other question comes up as we go along, then I'll be very happy to try and answer it. Okay, so the topic today is exponentials, and more specifically, this is a follow-up tutorial from a workshop there was one that was run last week, but there are many run throughout the year and all over England. And the topic of the workshop is exponentials, exponential functions, logarithms, and in particular sort of exponential processes. And we focus on the mathematics that goes behind it, that's universal to all these processes, but also on the interesting physics of all these processes. So because this is a follow-up from the workshop that we already ran, then I'm going to run through a couple of the harder problems towards the end. So I'm going to start with problem 8 about the bouncing ball. And then if time allows, I'm going to start covering problem 9 about money. And so if you haven't attended the workshop, chances are you might find this a bit tricky or confusing or altogether obscure. But don't worry, there's many other events that you can check out on our website on the events page that might be more suitable to you, or you can check for the next workshop on exponentials or vectors, which is another one we run, and send your application for it, and then come to visit us to do the workshop with us. Okay, so let's begin with the problem on the bouncing ball. So I'll share my screen with my tablet so that you can see my working. And please get your own sheet of paper and pen, because I only have this one screen to show you at a time, and I might have to erase things. Well, if you have your own notes, you're more likely not to get lost in the process. Okay, so I'll read the statement of the question. And again, please do send questions as you have them. I will check them periodically. Okay, so after a little investigation, it can be shown that the height of a bouncing ball can be expressed as a geometric progression. Quantities that increase or decrease geometrically are in fact exponential processes. This is, by the way, what we're going to find out in the question. The quantities change in direct proportion to themselves. Some algebraic manipulation can expose the natural exponential form. Okay. So a ball is dropped from an initial height h0 onto a table such that the height of the bounce is h1 equals alpha h0. Draw a diagram showing several bounces. So let's just do that straight away, because it's the fundamental initial step in tackling any problem in physics and many problems in mathematics as well. Okay, so let's draw a diagram. It's a very simple one. This is the horizontal table. I'm going to sort of draw a few snapshots of what happens, and sort of they're ordered in time from left to right. So it's not like this big line I drew is the time axis. But I'm just going to draw a snapshot from left to right. Okay, so this is the ball just before it is released. So it is at a height h0, which I'm going to label here. It is released, obviously travels down to the table because gravity is, of course, acting downwards. It bounces off one time on the table and then goes back up. Okay, and the maximum height it reaches after going back up is, let's say it arrives here, is going to be a bit less than h0. because energy is lost in stuff like heat and sound. And let's say that this new height is h1, and the text is telling us that this is equal to alpha h0. And by the way, on physical grounds, as I just said, h1 should be less than h0, so that means that alpha is a constant which is less than 1. So I'm going to keep it there. Okay, so this is the first bounce. What happens at the second bounce? Well, the ball will bounce up the table and then going back up, and will reach a maximum height, say h2. Well, how is h2 related to h1? Obviously, in the same way as h1 was related to h0, because h0, h1, and h2 are just names of things. So I can change them if I like. And in particular, h2 is going to be equal to alpha times h1. Okay, but h1 itself is equal to alpha h0, so I can plug that in again and get alpha squared h0. So this is the situation at the second bounce. What's going to happen at the third bounce, or rather after the third bounce? We're going to bounce back at a height h3, and once again h3 is going to be alpha h2, but then again, because of the expression for h2 in terms of h0 that we already obtained, we get alpha cubed h0. And so you can see where this is going to go. At the nth bounce, we have reached, after the nth bounce, we have reached a maximum height of alpha to the n times the original height h0. Okay, and we go on and on forever, in theory. Okay, part A says, using the properties, actually, sorry, let me just check if there are any questions about this. Okay, everything seems to be fine. So let's read part A. Using the properties of exponentials and logarithms, show that the height of the nth bounce as a function of n is hn equals h0 e to the cn, and give an expression for the constant c. Reassure yourself that this is a decaying function. Okay, so we've already obtained an expression for hn as a function of n, and I just have it here. I'm just going to put it inside the box here. So we already have obtained this expression, but we're being told that we should be rewriting this into this alternative form, where we have instead h0 times e to the cn. Okay, so we need to find a way for this to be equal to what we know for sure, which is alpha to the n h0. So the question is, can we find a c such that this equation is satisfied? I'm just going to link it by an arrow. Okay, so let's just write it out. We should have h0 e to the cn equals alpha to the n h0. Okay, h0 is obviously a non-zero height, so we can cross this out of the equation from both sides. So we're supposed to have e to the cn equals alpha to the n. Now, e to the cn, by the properties of the exponential functions which we studied last week in the workshop, is just equal to e to the c to the n. So in other words, I can, let me just erase this. I can just bracket the e to the c and then put the n here. Okay, which means that now I can take the nth root of both sides and just get that e to the c equals alpha. So how do I get c from this? Well, I just apply the natural logarithm. Why? Because the natural logarithm of e to the c is just c, because the logarithm undoes the exponential function. Therefore, c equals, applying the logarithm to the other side, natural log of alpha. Okay, so this is the final result. We can indeed write hn in the form required, provided that c equals natural log of alpha. So let's just write it out. hn equals h0 e to the c, which is natural log of alpha, times n. So if you like, this is in bracket, times n. Okay, we need to reassure ourselves that this is a decaying function. Yes, why? Because you might say, hang on, e to the something times n isn't that going to be an exponential function, and is not going to increase exponentially? Well, that would be the case if ln of alpha were a positive number, of course. But is it a positive number? Okay, so let's remember the graph of the natural log. It goes a bit like this. So this is, yeah, if you like, it's alpha versus natural log of alpha. It goes a bit like this. Where is it that it crosses 0? At 1. So if alpha is less than 1, then the natural log is negative. Well, but we were told right here at the beginning, or rather we reasoned by physics, that alpha is less than 1. Therefore, this natural log is actually a negative number. So we have e to the something negative times n, which is an exponentially decreasing function, which is what we expect, right? Because we expect the height after the nth bounds to get smaller and smaller. Okay, so this is part A. Let's see if there are any questions. Okay, all seems okay. So let's go to part B. How far does the ball travel before it stops bouncing in the ideal case? Why might this distance not be attained in practice? Okay, so I'll actually need to redraw at least part of the diagram. So this was h0. Okay, let's just draw h0 and h1 for now. Actually, and h2 as well. Okay, and we've learned that hn equals alpha to the n h0, but also h0 e to the cn e to the 1 ln of alpha n. Okay. So we're thinking about how far the ball travels before it stops bouncing. In other words, the total distance traveled. Okay, so what do we need to do? We need to sum up all the distances traveled in all the sections of this process. Okay, so the ball falls for a height hn to height 0, where the table is. Then it bounces back to height hn plus 1, falls again back to height 0, and so on and so forth. So in particular, after the nth bounce, okay, so after the nth bounce, the ball travels a distance hn upwards, and also hn downwards, of course. So all I'm saying is if I add the position of the ball after the first bounce, okay, so the first bounce would have sort of occurred somewhere here. Okay, this is the first bounce. Then the ball would have traveled h1 up, and then it falls back again. Okay, so this is the first bounce, and this is the second bounce over here. Okay, so we can, and okay, the h0 is an odd one out because there's no bounces before h0, so we only have one lot of h0, if you like. But other than that, this means that the total distance traveled, let's call it h. Okay, so first thing we do is we travel h0 down, then we travel h1 up, and then h1 down again, so a total of 2h1. Okay, and similarly then we travel h2 up, but then h2 down again, and so a total of 2h2, and so on and so forth. Okay, so we have ended up with an infinite sum. Okay, at least in the ideal case. We're going to discuss later why in practice this is not going to be an infinite sum physically, but mathematically this is what we have. Okay, so we need to calculate this, and it seems it's a little bit awkward because there are 2's everywhere except in front of h naught, but we can just make the 2 appear in front of h naught by force. By doing this, we just write 2h naught instead of h naught, and then keep the rest the same. But then we need to compensate by subtracting out h naught at the end. Okay, so now we can factorize the 2 and end up with 2 into h naught plus h1 plus h2 plus dot 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 minus h naught. Okay, but now let's remember, h1 is just alpha h naught, h2 is just alpha squared h naught, and hn in general is alpha to the n h naught. So let's just use that. What do we end up with? We end up with 2 into h naught plus alpha h naught plus alpha squared h naught plus dot 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 minus h naught. And so in beta we end up with 2 h naught into 1 plus alpha squared plus dot 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 minus h naught. Okay, so now we have a very simple looking infinite sum inside those curly brackets. So let me call that infinite sum S, and many of you will probably recognize it from your maths courses. It's called the geometric series. Okay, but in case you've forgotten what the value of the sum is, let's just do it very quickly again. It's not hard at all, and it's quite a nice derivation. Okay, so let's say that S equals 1 plus alpha squared plus dot dot dot. What happens if I multiply both sides by alpha? Okay, so alpha S equals alpha plus alpha squared plus alpha cubed plus dot dot dot, multiplying the right-hand side by alpha. But this right-hand side looks fairly similar to what S already was. It's just that we're missing the first one. So that means that the right-hand side is now just equal to S minus 1. So as you can see, just by multiplying both sides by alpha, we've got a very simple equation here that S satisfies, which is that alpha S equals S minus 1. So let's just solve that. It's very simple. We get S into 1 minus alpha equals 1. Therefore, S equals 1 over 1 minus alpha. And of course, this makes sense because alpha is less than 1, and it is also greater than 0. So we get a positive number. Okay, so this is what the infinite series in the round brackets is equal to. So we can just plug in the result now. So let me just erase the first few lines, not the last one. We end up with h equals, well, it's equal to 2h naught into that sum. So 2h naught over 1 minus alpha minus h naught. So let's just clean this up a bit. We have 1 minus alpha 2h naught minus h naught into 1 minus alpha, so minus h naught plus alpha h naught. Which then equals to 1 plus alpha into h naught over 1 minus alpha. Okay, so this is our final result, and this is the total distance traveled. Why is it that in practice is not attained? Well, that would mean there's an infinite number of bounces, and as we will see in the next section, it would mean that once the number of bounces gets really, really high, the ball will start, the time difference between any two given bounces would be very, very small, okay, and it might become so, eventually will become so small that it will be comparable with the speed of sound of the material that we're using. So the material doesn't have the time, as it were, to compress and extend at the speed required to keep up this constant bouncing. Okay, so there's also, of course, going to be dissipations, there's going to be air resistance, there's going to be energy losses by sound and heat, which are other reasons that this will not actually happen. But mathematically speaking, this is the result. Okay, so let me move on to the next. Well, let me check that there are questions, and then move on to the next part. Okay, all seems good. Part C, find the time between the nth and n plus first bounces. Show that it can be written as 2t0 e to the minus beta n and give expressions for t0 and beta. Find the total time spent bouncing in the ideal case. How many bounces does the ball execute in this time? Okay, so again, just drawing one bounce here, hn. Okay, so we want the time between the nth and n plus first bounces. So actually the nth bounce happened somewhere here. Okay, and the n plus first happens somewhere here, and then we reach height hn. Okay. hn plus 1, excuse me. Okay, so what is the time between the nth and n plus first bounces? Well, that means the time between this event and this event. So we need to look at what happens in this sort of time frame. Okay, so the ball certainly, let's first actually look at what happens between here and here. So between the point of maximum of height hn and then the time at which the ball does its n plus first bounce. Well, the ball just is falling down from an initial speed of 0, of course, meters per second, let's say, to the ground, and is being accelerated purely by gravity. Let's say that there's no air resistance. So it's quite an easy calculation using the Suvat equations of motion. Okay, so in particular, we use this Suvat equation of motion. S equals ut plus 1/2 at squared, where u is the initial speed and a is the acceleration. Okay, but let's use it in our situation. Well, in our situation, we're looking at the time frame here. We know what s is because the ball will of course will have traveled hn down. We know what u is because it starts with 0 speed, so equals 0. So we're only left with 1/2 at squared. A is of course g, because gravity is the only force in the problem. And then we have this t squared. Okay, and so let's call this, yeah, well, let's just call it t squared for now. So this just gives us, by rearranging, that t equals the square root of 2hn over g. So this is the time that it takes from when the ball is at height hn to when the ball does its n plus first bounce. Okay, but of course, before the ball was, and also, sorry, let me just add something else to this, which is that, of course, we can now use the relation we already knew for hn. Of course, we knew that hn was alpha to the n times h naught. So actually, we can write this t in terms of just h naught as square root of 2 times alpha to the n h naught over g. Or in other words, alpha to the n over 2 times the square root of 2h naught over g. And let me call the quantity in the square root, or sorry, rather the square root itself, t naught, for I hope obvious reasons, because it is the time that it takes from the initial height to the first bounce. So we get an expression like this. Okay, so in the same way that we had the time, the distance for the distance after the, sorry, the maximum height after the nth bounce, just in terms of h naught, we have this time just in terms of t naught and alpha. Okay, so this was just the portion that I've highlighted in the curly braces on top of the diagram over here. But of course, the half that came before that, okay, between the nth bounds and the point of height at which the ball is, the time at which the ball is at height hn, by symmetry, the ball will have taken the same time to travel upwards to hn. So basically, the total time taken by this reasoning let me call it t. Okay, we have an initial t naught, which is what I wrote over here. And there's only one of those, but then there's two of each of the other t's. Okay, so 2t1, 2t2, dot, 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 dot. Okay, and sorry, I forgot to, I should have called this tn. Okay, but there's two of these tn's. Okay, so we have a very similar situation to what we had before. So let's do the exact same trick. Let's rearrange this a little bit. We first sort of create the 2 by hand in front of the t naught. And then we have to compensate by removing t naught. Okay, so, but then we have an expression for tn as a function of alpha and t naught. So let's use that, and we end up with 2. Well, we can take the 2 out for sure, and then we have t naught plus alpha to the 1/2 plus well, maybe I should be writing to be neater, square root of alpha. And then we have square root of alpha squared for t2. Sorry. Okay, I forgot to write the t naught earlier on here, and I need another t naught here. Plus, then we go on like square root of alpha cube t naught plus dot 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 minus t naught. Okay, so we can take the t naught out in a similar way as before, and we end up with 2 t naught 1 plus square root alpha plus square root of alpha squared plus square root of alpha cube plus dot 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 minus t naught. Okay, so we are in a very, very similar situation to what we had before, except instead of alpha, we have square root of alpha. But then, so earlier we had this formula that s equals 1 over 1 minus alpha for the geometric series. But here, instead of alpha, we have square root of alpha. So if what I have in these curly brackets is now s, or maybe let's call it s prime just to be a bit clearer, then s prime this time is equal to 1 over 1 minus square root of alpha. Okay. So then we end up with 2t naught over 1 minus square root of alpha minus t naught. And yeah, in principle, you might say, okay, well, this is just this is just the this is just it. This is the final expression already. Let's just clean it up a little bit. We end up with 1 minus square root of alpha at the bottom, and then at the top, 2t naught minus t naught plus square root of alpha t naught. And in the end, we have a very similar expression to the one earlier, except instead of the alphas, we have square root of alphas this time, and instead of h naught, we have t naught. Okay, so this is our final answer. So let me check if there are any questions. Okay, everything is fine. Yes, so we want now well, we're being asked what is, so I guess I haven't quite covered the second sentence, which was show that it can be written as 2t naught e to the minus beta n for what I call the tn. But this is a very simple exercise, a lot like part A. So I hope that you can do that yourselves just in the same way as I did part A of this exercise. So let me get to the more interesting part. This is the total time spent. How many bounces does the ball execute? Well, we already discussed this basically. Ideally, in the ideal case, the ball executes an infinite number of bounces in this time. So it's quite interesting. Notice that this time is actually finite, okay? Because 1 plus square root of alpha or 1 minus square root of alpha times t naught is a finite number because alpha is less than 1. However, there's an infinite number of bounces in this time. So, it's a bit of a strange thing to occur in real life, and luckily you don't need to get too worried about this because, as we discussed already, actually this cannot quite happen in real life. We're going to stop after a certain number of bounces because of all these issues about the material not being able to compress and extend quite fast enough, and also some resistances we might have. Okay, so that was part C. Let's just do part D now. Calculate the frequency of bouncing heard as a function of bounce number n and also of time tn at the nth bounce. So this is quite a simple exercise given what we've already done. The frequency at bounce n is going to be given by 1 over 2tn. Why? Because 2tn is the time, so this is the time between the nth and n plus first bounce. And the frequency, of course, is the inverse of a time. And so we just have to take the reciprocal of 2tn. So we calculated earlier that tn was equal to alpha to the n over 2t naught, where of course t naught was, let me just remind you here, t naught was the square root of 2h naught over g. Okay, so in particular, fn can be written also as 1 over 2 alpha to the n over 2 t naught. Okay, so this is the expression for the frequency of bouncing, suddenly as a function of bounce number n, because the n appears as a power of alpha. But now the question is asking in the second part to have this as a function of time tn at the nth bounce. And I don't mean the time between any two bounces. I mean the time that you would read, that you would have on your clock at the time of the nth bounce. Okay? So we need to now calculate this tn in general. Okay, so what is the time at the nth bounce? Well, we calculated the total time that it takes for the ball to bounce infinitely many times. So the time at the nth bounce is just going to be a part of that total time. So we're going to have the same formula as before. T naught plus 2t1 plus 2t2. But this time it's not going to carry on forever. It's going to stop at some point. It's going to stop at, and I need to think a little bit about it. Do I need to write a tn here, a tn minus 1, or tn plus 1? I need to write a tn minus 1 because this is 2tn minus 1 is the time that it takes between the n minus first bounce and the nth bounce. So at the end of this time, we are at the nth bounce, and what we want is the time at the nth bounce. Okay, so, but other than that, we do exactly the same, again, manipulation as before. So let me just repeat it. Okay, same kind of manipulation. We remember the expression for t1, t2, t3, and so on in terms of t0. We take the t0 out, so I'm going to do it in only one step, and we just end up with the same thing we had before. It's just that this time we don't go on forever, but we stop for square root of alpha to the n minus 1. Minus t0. Okay, so I don't want to remove the fun from this exercise, but it is exactly the same technique as we did earlier on. You call this guy, let me call it S again and not worry about primes. Let me call this guy S. You write that S equals 1 plus square root of alpha plus square root of alpha squared and so on, except this time it stops, as I said. Then you multiply both sides by alpha. You rearrange things a bit. This time you're not going to just have to subtract a 1, you're also going to have to subtract an alpha to the a square root of alpha to the n. Okay, but other than that, the calculation is exactly identical. Let me write the final result. You end up with, so actually I should probably be calling this Sn instead of S because it depends on n. So if you calculate n, you will find it to be Sn equals 1 minus square root of alpha to the n over 1 minus square root of alpha. Okay, so you plug this in into the expression for Tn, and you just end up, after a bit of rearrangement, with T0 times 1 plus square root of alpha minus 2 square root of alpha to the n over 1 minus square root of alpha. Okay, so this is the expression for Tn in terms of alpha and n. But we wanted the expression for, we wanted to relate now Fn with Tn, which is now calculating like this. So basically, instead of this term alpha to the n over 2, we want to be putting a Tn. Okay, so how do we get that? Well, one way is to say, let's just look at the equation we ended up with, which is, so let me just rewrite the Tn here. Okay, so starting from this equation, you see we have an alpha to the n minus 2 over here. It's the last term on the numerator of this fraction. So let's just isolate this, and then we'll obtain the expression in terms of Tn. So we have the Tn, so rearranging things a bit, into 1 minus square root of alpha over T0 equals 1 plus square root of alpha minus 2 square root of alpha to the n, and finally 2 square root of alpha to the n, which is obviously nothing but alpha to the n over 2 equals 1 plus square root of alpha minus 1 minus square root of alpha Tn over T0. So I've put the 2 square root of alpha to the n to the left, and then everything else to the right to get this result. Okay, so without, well, okay, let me just finish this off. So I'm just going to plug this result in here. We wanted the expression for Fn in terms of Tn, so I just calculated that alpha to the n, what 2 alpha to the n over 2 is in terms of Tn, so I'm just going to plug it in, and I get 1 over 1 plus square root of alpha minus 1 minus square root of alpha Tn over T0. Let me just erase the rest so that it's not too much stuff. Okay, and of course we could have already known this from earlier, but this expression shows you that as a time tends to the maximum total time. Okay, remember that the maximum total time was t equal t naught 1 plus square root of alpha over 1 minus square root of alpha. So as Tn tends to this, which is its limiting value, then as you can see, you will see that the denominator tends to 0, which means that one of the denominator, which is Fn itself, will tend to infinity, so the frequency will go to infinity. Of course, you didn't need to go through such lengths to discover that. It was sufficient to look at the first equality, because if Fn equals 1 over, so let me write it separately, if Fn equals 1 over 2t naught times 1 over alpha to the n over 2, because alpha is less than 1, and this is the same as saying 1 over 2t naught and then 1 over alpha to the n over 2, of course. But 1 over alpha, because alpha is less than 1, 1 over alpha is greater than 1. And if you look at, well, okay, let me simplify, and also square root of 1 over alpha is greater than 1. So I have something like 1 over 2 t naught square root of 1 over alpha, which is a number which is greater than 1 to the n. And when you look at the sequence, when you have a number greater than 1 to the power n and you let n tend to infinity, this will give you in the limit infinity. So we could have already known about the frequency by that simpler equation. Okay, so there isn't much time, almost no time in fact, left for anything else, unless there are final questions. But let me just tell you one thing that might unlock you a little bit about the question on money, in case you haven't been able to get started with it. I'll just very quickly read the question. A sum of money n is invested with an interest rate r. Banks can choose how often throughout the year to calculate the interest and whether or not to compound the interest. For example, interest might be calculated annually, quarterly, monthly, or continuously. If r equals, so this is part C in exercise 9, if r equals, let me write it, r equals 10% per year, so write in units like physicists, e to the minus 1, by how much does your capital increase after 10 years if the interest is compounded? Okay, let's do part 1, quarterly. Part 1 is quarterly. So this means, what does this all mean? The interest being compounded and so on. We have a rate that's 10% per year, but and we let the interest increase up to a quarter of a year at that rate, at which point we pause, we calculate what interest is due at that time, and we add it to the total capital. And then we let time run again and repeat after another quarter. So what is the fundamental thing to realize here? It is that without compounding, so I think I'll finish this off here. Without compounding, if money is invested for t years, so t is just a pure number, but it gives you the time in years, okay? Years. The interest gain so we're going to think about what is the interest gain in that case. So we call it I, okay? So obviously the interest is proportional to the initial capital, so M0. And it is proportional to the interest rate, which is R, okay? And if the interest rate is measured in years to the minus 1, as it is in this, and t is measured in years, then all you need to do is multiply this by t as well. If the units for the interest rate were different, you'd have to use to measure t also in those different units. You'd have to convert everything to those other units. And so in particular, the total capital is, let's call it m, going to be by m naught, which is what you had at the beginning, plus the interest. So m naught into 1 plus RT. So this is the fundamental thing to realize. And what does compounding mean? So with compounding, let's do quarterly compounding. What does it mean? You let the interest sort of grow and grow for a quarter of a year. Okay, so what does that mean? It means that t in the expression I had above is equal to 1/4 a year, of course, but a t is a dimensionless number, so I'm not going to write years. So that's 0.25. And at that point, you stop. So after a quarter of a year, you stop and calculate, let's say, m1. Sorry, actually, m1 might be confusing because it might mean 1 year. Instead, I mean after the first quarter. So let me write m14, 104. This is going to be, just from the expression we had above, m naught into 1 plus RT. Okay, R is 10%, so we need to write 10 over 100. Okay, times t, which is 0.25. Okay, so simplifying this a bit, we end up with n naught times into rather 1.025. And so what happens if you, what happens after n quarters? So after n, a number n of quarters, well, you're going to have m, you know, I should write something like m n over 4, but I'm just going to write m instead. Well, at the second quarter, you would have, so let's just write this for a second. What's m of 2 quarters? Well, it is m of 1 quarter times that very same factor that we just found, which is 1.025. So it is just m naught into 1.025 squared. This means that in general, after n quarters, we have m naught into 1.025 to the power n. So all you need to do for the rest of this exercise, in part 1, you're being told that you're looking at a time period of 10 years in total. So just ask yourselves how many quarters are there in 10 years. Of course, there are 40 quarters. So all you need to do is to put the number 40 in the place of n. Okay, so just do it very quickly to wrap up. You end up with so actually, sorry, so 10 years equals 40 quarters. So that m will be, in this case, m naught into 1.025 to the 40. And this number ends up being approximately 2.69. So times a naught, which means that m over m naught equals 2.69. So, which is of course 1 plus 1.69, which in particular means that the capital has increased by 169%. Okay, so the entire rest of this exercise on money is based on this sort of procedure. But it's interesting that you will notice how the Euler's number E naturally crops out when you go to finer and finer and finer periods of time after which, I should say, sorry, shorter and shorter periods of time after which the interest is compounded. And this is in fact more or less how historically the exponential function, or one way in which the exponential function was used and discovered historically. So it's a very interesting exercise to go through. Okay, so I hope, just do a quick look for other questions. There seems to be none. So I hope this was useful to you. And hope in fact to see you soon, both for other online tutorials like this and for real life events, to which you're all very welcome. And we hope you find the rest of the site useful, and see you soon. Goodbye.